Yeah, I mean, it's laughable what is, tried to pass off as, and you know what's so great now about YouTube and about these video platforms is, back in the day, you got one shot to see this stuff on television, and that was it. I mean, you believed it was true. You saw it once. Maybe you saw it on a rerun. Maybe on the other news channel they would rerun some of this footage. But now it's all been released, and people have the ability to look at it and to pick it apart and to really think about it. Like we talked earlier about the lunar landing. Now that people have the technology at their fingertips on their laptops to be able to speed up the lunar landing footage. You have the Land Rover going around, and you have the guys hopping around in slow motion. Speed that up 200%, and it looks like they went out in the desert and filmed that. But here's something that I'm going to tell you as a video guy. Here's why I believe that the lunar landing was faked. Because there is no way you can have a power source that strong at that time in history, and there's no way you could transmit that video signal all the way to Earth. Absolutely 100% not. Let me tell you something. I have just on my, if I have a handheld video camera and I want, and let's say I'm shooting a scene and the producer wants to see what I'm shooting. So they have a transmitter in their hand and they have a battery on my camera. The battery that I have is about the size of a brick. It's more square, but it's about the same mass as a brick. And it only lasts for maybe an hour and a half. And that signal only goes a couple 100 feet. Now you're going to tell me that on that teeny little spaceship, with that teeny little camera, they're going to have enough power to transmit a full color video signal all the way down to Earth. And I can also tell you this, that when they promised a full color video signal, the station that broadcasted the lunar landing, they were pissed because they weren't getting raw video feed. What they were getting was called a kinescope. And for those of you who don't know what that is, that was an editing process used up until the late 1990s. And I've actually seen the kinescope technology and utilized it when I worked in a film lab, and it's very interesting. Basically, it's an editing tool. So you have a screen, basically it's a television screen, and you shoot that with a film camera. So now it's on 16 millimeter film. So what they did with those videos, in theory, why you see a black and white image of the lunar landing, although they claim the full color videos exist, was what NASA says they did was transmitted the full color video signal, filmed it on a kinescope, black and white on 16 millimeter film, and then released that to the networks. So therefore, it was not a live event, because to get film processed, it takes hours, and it's a whole process that generally takes about 6 hours to complete, even with the most efficient film laboratories. So why would they get this crappy, grainy, black and white film image when they could have broadcasted color, which at the time the networks were pissed that they didn't have the ability to do, that NASA denied them? But anyway, that's neither here nor there. The whole kinescope thing, that's a side note. My thing is, there is no way with that technology and with batteries being as big and as weak and as heavy as they were, you could have broadcast that signal from the moon. Impossible.
because honestly, as an RF engineer, I look at this now and I'm like, how in the hell did I miss this? Well, I missed it because of my indoctrinated thinking, just like I missed the impossibility of 60 to 100 mile microwave shots because of an alleged curvature of the Earth. We were making them, but the curvature of the Earth absolutely prohibits that from happening. Something I never thought about, something I guarantee you that no other RF engineer has thought about, or if they have, then they're probably not going to be going to their boss and telling them, hey, we got a problem here, this shouldn't be working, because they'd probably be fired. You know, I'm sure you all understand how that works. All right, so the next thing we're going to do is, because we're not dealing in watts, which we're so used to using in our transmit power, we're going to be converting watts into decibels, okay? Now, you have two basic figures that are used in decibels. You have dBm, which means decibels with reference to 1 milliwatt, which is 1/1000th of a watt. And then you just have simple just dB, okay, which dB watts, which would be the watts, okay. So basically, if we have 1 dB, there's basically a 30 decibel difference, okay, between dBm and dBw. So if we say 30, goes back to 0. 30 dBm is 0 dBw, okay. And this is gonna get really clear here in just a minute. So what I'm going to do, first of all, is we're going to take this free space loss calculator and we're going to find out how much power we have to be able to transmit over certain distances, okay? And again, this is all handy dandy, it's wonderful, all calculated for us. And as you can tell here, I have already done a calculation of 250,000 miles, and I'm sure anybody that thinks about that would be equal to a one-way trip to the moon. All right, now hams cannot put any more than 2,000 watts. They are limited to 2,000 watts, okay? And they may be able to get a gain figure of 6 to 9 dB. So again, going back to our rule of thumb, if we have 2,000 watts maximum power input, which gives us maybe 1,500 watts at best output, and we give that through 9 dB, so we're tripling that power. So we go 1,500 watts to 3,000 watts is 3 dB, 3,000 watts to 6,000 watts is 6 dB, and 6,000 watts to 12,000 watts is 9 dB. So we have 12,000 watts ERP, all right? All right, so basically what this is saying is this is a 70 dB maximum power output, even with the best of circumstances. So let's go back to this. Transmitter gain, 70 dB. All right, receiver gain, let's give it I don't know, let's give it that same 9 dB. Calculate it. Free space path loss is 108 decibels, okay? So what does that mean? That means to overcome this 108 dB loss of power, now we have to go to dBW, and let's put in 108, convert it. That means that we have to have a transmit power, and you can see this is a big number, 448,734. So we're talking about 63 billion, 95,734,448 watts.
Jeez.
Just to overcome the path loss. All right? Do you see a problem here? And this is only going one way to the moon. All right? Now let's look at something really ridiculous. Okay? Let's look at a distance, and let's all of a sudden now let's go to NASA's frequencies, and let's go to 10 gigahertz. All right, and let's say that they're transmitting, I don't know, and then we know the satellites can't put out a whole lot of power because they only have solar arrays on them. So let's say those solar arrays maybe are capable of delivering, let's say, 10,000 watts, which is absurd. You know, we can just apply a little bit of common sense here to this. All right, so transmitter gain, again, let's give them the benefit of the doubt and say that they can run 10 kW. That's going to be 70 dB. All right. So 70 dB. And now let's go to, I don't know, let's go to the sun. All right. The sun, and the reason the sun is not an unreasonable example, because what, Jupiter is a lot further away, right? Stuff like that. So let's just do a shot to the sun. 93 million miles, 10 gigahertz. There's our power. Let's give them the advantage of having a high gain receiver antenna, and let's give them let's give them 20 dB of gain there. All right, calculate. Now we're talking about a free space path loss of 185.9 decibels. Well, let's go back to our decibel converter. So let's go 185 dB, which means that to make the trip to the sun, now we have to have, oh my, this is such a big number, I don't even know what it is, but it's in the petawatts, okay? You're getting the idea here, guys. In other words, there is no freaking way on God's green earth that we can be making transmissions of these distances, given the idea of how much power is on board these satellites. All right? I think, and of course there are other factors, yes, there are other losses, there are other gains, whatever, but this is a very, trimmed down version to simply show you, even if I'm off by a factor of 1 million or even 1 billion, it's impossible. It is impossible to make these journeys at these distances, okay? This is the point that I've been talking about all these times. I have just used all mainstream sources, all mainstream information, everything, and I have shown, even in a physics lecture, how all of this works. The impossibility of transmitting a signal, it can't even be done to the moon, all right? Especially with what the hams can do. So what are the ham radio operators talking about when they say, well, we're doing these EME bounces? Well, first of all, EME bounce, if you're talking about a 250,000 mile trip, that means that you've got a 500,000 mile or 500,000 mile journey, that this limited power that the hams can use to go up there and bounce back. As I've just shown, this is patently impossible. So what is it that they're bouncing these signals off of? Well, there's something that reflects RF radio waves. You can call it the ionosphere, whatever you want to call it. That is what it is that is reflecting these signals back. So yes, they honestly do believe that they're doing it, but as I have just shown, using all mainstream calculations and all mainstream science, the impossibility of it goes beyond silly, right? I mean, there's just no way that we can make these types of broadcasts, and common sense tells you that here on good old plain Earth, because if we have 50,000 watts and a relatively high gain antenna for AM radio station KOA, and we can barely cover the state, all right? Now we're starting to put things in perspective, all right? This is what I have been trying to tell people, and again, there are several other factors, but believe me, nothing that's going to make 1 million or 1 billion times difference in these calculations. Do the calculations yourself, look up antenna gain factors, and also how far down in the mud or signals can be retrieved from ground noise level. And typically, a typical receiver sensitivity is minus 100 dBm, okay? So that's typical, some a little more, some a little less, depending on the frequency again. All these are factors, but the bottom line is that no matter what frequency they're using, and they would be far better off using low frequencies than they would be microwave, but even they won't make the distance, even though they have considerably less path loss.
I'd go to the moon in a nanosecond. The problem is we don't have the technology to do that anymore. We used to, but we destroyed that technology, and it's a painful process to build it back again.